Welcome to the second presentation in the inaugural webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all the attendees, families, and colleagues are safe amid the ongoing COVID-19 pandemic. Today's webinar will be presented by Professor Andreas Seidel-Morgenstern with moderation of questions by Professor Arvind Rajendran and Nick Wilkins, both of the University of Alberta. I'm Daniel Sidarius of the U.S. National Institute of Standards and Technology and the Secretary Treasurer of the IAS, and will serve as the webinar host. We are required to remind attendees and future viewers that the views expressed by the speaker, host, and other moderators are not necessarily those of the IAS or the institutions associated with those individuals. Any mention of commercial products during this webinar is for information only. It does not imply recommendation or endorsement by those individuals or their associated institutions. The full disclaimer statement is shown and will be included in the archived video of this webinar. We ask that you consider joining the IAS as a regular member if you're not already. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS Twitter at @intadsos for future updates regarding IAS events, webinars, and information about scientific meetings. Please expand our YouTube channel by subscribing. During today's webinar, questions can be submitted to the speaker via the Q&A tab of the Zoom client or as comments on YouTube. Those comments will be forwarded to the Zoom hosts. Our speaker will take questions at certain points and then at the end of the webinar. And now I'm pleased to introduce today's speaker, Professor Andreas Seidel-Morgenstern, a director of the Max Planck Institute for Dynamics of Complex Technical Systems in Magdeburg and chair of chemical engineering at Otto von Guericke University Magdeburg. Professor Seidel-Morgenstern is widely known as an expert in process engineering with particular interest in heterogeneous catalysis, adsorption, and preparative chromatography and crystallization. Additionally, he is the current president of the International Adsorption Society and was the organizer of the 10th Fundamentals of Adsorption meeting held in Germany in 2016. Today, he will present work and his thoughts on quantitative connection between adsorption isotherms and retention times of breakthrough curves. And at this point, I'm going to hand control over to Professor Seidel-Morgenstern for his presentation.
So let me just test. Hello, everybody. I just shared my screen and want to see if I can move it. Yeah, so it's working well. So good afternoon. I'm in Germany. It's 4 p.m. here. I don't know where you are listening. I'm very glad that I have this opportunity to present some connection between adsorption isotherms and front propagation speeds or positions. So in short, to breakthrough curves. You know, this is in the field of adsorption a very essential part of the process development, which starts actually with materials design. Then we characterize the materials, their storage capacities by the isotherms. We want to use them very often in fixed beds where we have kinetic phenomena and this dynamic features, how fronts propagate, how these components separate from each other, and multiple process options show up then. In the middle part is the topic of my lecture today, and I consider this to be a really integrating part between the material scientists and the process engineers. And to have here a good quantitative understanding is essential for the development of important processes like maybe Marco has explained yesterday, important example, and there are many of them. So let me start shortly by introducing myself. I'm a German chemical engineer, East and West German background, East and West Berlin experience, and I met breakthrough curves already during my PhD in the form of activated carbon as an adsorbent for drinking water. I recorded such S-shaped breakthrough curves for phenol for different activated carbons. In that time, I learned also that there is a connection between the shape of the isotherm and the shape of a breakthrough curve. That's the topic of today. And it's a long time ago. You see, I'm involved in that business, and it's around. And now in Magdeburg, the city where this famous experiment with the vacuum was done, we have adsorption classes. And I was recently asked by a German journal, the Chemie Ingenieurtechnik, to write a small primer, rapid estimation of breakthrough behavior components. So essentially, the slides will come partly from this paper, and to being short of time in this Corona pandemic period, I have still some slides with German notation, but they will be easy to understand for you. On the top, you see the downtown East Berlin in the time before the wall came up. This Parliament of East Germany does not exist anymore. Of course, sculptures of Marx and Engels are around, but for me it's important to give an acknowledgement and a credit to Georges Guichon and Peter Hugo, which were my supervisors and professors in certain periods of time. So Corona, Dan mentioned it, is around. There you see also the progress curve, incredible large numbers, incredible difficult to predict. It looks a little bit like an S shape. The breakthrough curves that we have here that we want to model with adsorption isotherms as one essential ingredient share similarities. We are a little bit on an easier side. To explain a breakthrough curve is by far easier, obviously, than to understand how these curves will develop and how we finally reach some hopefully good saturation level. So let's start with a few isotherm pictures. I have to say that my examples will be mostly or exclusively today from the liquid phase. We do a lot of work on chromatography using liquid phase adsorption phenomena, and that I will use for illustration, although the aspects I want to address are true for gas phase adsorption as well. Here we see for aromatic compounds on and reversed phase silica used often in chromatography in mobile phase methanol water 50-50 at ambient temperature, 3 isotherms. They were measured by analyzing breakthrough curves, so solving more or less the inverse problem. You see a lot of points, not so precise at some points, not easy to measure. We see a certain degree of nonlinearity, and we need to describe, to be quantitative, these courses. The typical notation that I will use is Q for the loadings and C for the fluid phase concentration. Here, the concentration in solution. It can be in the gas phase partial pressures, for example. Everything is constant with respect to temperature. We talk about isotherms, and we have many models in this area. A huge field, big progress, but still many difficult questions. For new systems, it's hard to predict the isotherm precisely. Among the many models, the most popular is obviously the Langmuir model, very old and very successful. I write here the single component Langmuir equation down, which has the 2 parameters in saturation value and in nonlinearity capturing parameter B, which is obviously temperature dependent, but for a constant temperature, we have this value again as a constant. So these are isotherms, and if we use one of these systems, in this case phenylethanol, where we now know the isotherm, and we inject or we dose on a fixed bed. In this case, it was a relatively small fixed bed, an HPLC column, different solution concentrations. This is a series of increasing the solution concentration. And we do it quite some time. If I remember right, the injection time was something like a few minutes. In any case, we reached total breakthrough. So the initial part here is always, is always the breakthrough curve. Then we have the constant plateau value connected with the feed concentration here, just expressed by a UV detector signal. And at a certain point, we start to desorb. And then we see these waves forming. The desorption fronts are dispersed, not as sharp as the adsorption front. So this is a very typical phenomenon, and it's a clear indicator that we have Langmuir type of adsorption isotherms. So there is a connection between the shape, the position of these fronts, and the isotherm shape. Let's go the next step to mixtures. What happens if there is not only one component in the system, but many of them? So here we have in the dashed line the three isotherms that we saw before now regressed with the Langmuir model. This is the single component behavior. And the dots for these three systems now indicate always the competitive loadings reached in 1-1-1 ternary systems. And we see the degree of competition clearly. And we have now the task to describe these mixture data. And this is again a huge field. And staying simple, I write here again the competitive Langmuir isotherm down, where now in the denominator, the competition, the presence of the other components is suppressing the loading of a given component I. This is a good theory, but very often not very precise. We have better alternatives, and I just mentioned here the famous ideal adsorption solution theory by Myers and Prausnitz, which could generate mixture behavior. So that's what we need. And this will be then needed to predict competitive breakthrough curves. Here is a nice example coming from a literature source from a Taiwanese group, again in the liquid phase on activated carbon, phenol and paranitrophenol together, not in a 1-1 situation, but there is an excess of phenol. You see it in the final equilibrium value. But what is interesting here is this overshoot of the first eluting component, the phenol, which has a higher concentration for a certain time than the fat concentration. And we see there is a quite steep increase here. And also the second transition is relatively steep. The lines given here already anticipate what I'm going to explain soon, that there are theories around just based on the isotherm knowledge that give very, very good the corset, so to say, the shape of these breakthrough curves. In this particular paper, you can find the application of single component Freundlich isotherms combined in the IAS that I mentioned, and then using the equilibrium theory of fixed beds, which I will explain in a minute. And you see there's a nice agreement. Isotherms and breakthrough curves are well connected. So what is the task of my lecture, or what do I want to discuss with you? We want to bridge this gap. We need this, in fact, because adsorber design, performance evaluation needs very much to understand the position of fronts in adsorber. Very clearly, if you have an isotherm which for a single component is characterized by higher loading, more storage capacity, as here the red curve has significantly higher loading than the black curve that could be different adsorbents for the same single component. The red curve will the red adsorbent, so to say, will retain the components longer, and we have maybe more fun with the adsorber. We don't need to regenerate it too often. We can, if we give a specific size, a specific time for retention, we can then design the adsorber that it is long enough. All these things are the important engineering tasks to be solved to apply adsorption in an efficient way. So the quantitative description concerns this question mark here. And so I give you basic equations, which I cannot explain for the sake of time in all details. I guess most chemical engineers know them very well. Among the material scientists that produce materials, maybe that's not so familiar and not so often used. Let me go quickly in the mass balance of a fixed bed, which you see here as the first equation. Now, this is a partial differential equation, a differential mass balance where in time t and in space x, it's just a one-dimensional view in a tube, in a column, characterized by the coordinate x, where there exist two phases, namely our fluid phase with a concentration C and the phase stored in the adsorbent, the loading phase or the adsorbed phase characterized by the Q. There is a movement of the fluid phase with a velocity u, the convective term. The solid phase does not move. We talk here about a fixed bed, not a moving bed. And in the fluid phase, typically there is some dispersion, some backmixing, which spreads the bands. This is now a coefficient which we can use. I will not go much deeper in kinetics as an effective dispersion coefficient, which captures all band broadening kinetic phenomena. And we can substitute it by maybe, or this equation by more complicated kinetic equations capturing more mechanisms. These equations are known, they are used, but for my purpose today, I just say there is a kinetic effect broadening the bands and characterized by one coefficient. This coefficient in chromatography is very often correlated to the number of equilibrium stages a fixed bed or a column has inversively. This is the well-known correlation between these two. For my purpose today, I go further in this simplification. I say there is no kinetic effect at all in the beginning. We call this the equilibrium theory, leaving this effect zero. And then we can analyze this now first order partial differential equation, a hyperbolic first order partial differential equation results where a strong theory is available. More or less a complete theory of this equation can be used. So then let's do that. I should mention this F is just a phase ratio. It tells us the porosities, how well the column is packed, how much of the solid is inside, and how much of the liquid. So the solution for a single component system where we just look at a single component isotherm is very easy. It's in particular easy, and that's in my next slide, the next assumption, which is strongly valid in liquid phase and very questionable and should be checked in the gas phase if there is strong adsorption. I will take in the next slide the velocity u as constant, so I can take it out of this differential. By the way, I have maybe my pointer not activated. I will not do it now, as I think you see it. I'm talking about the U constant, and you see it in the mass balance on the top. So rearranging this equation for a constant concentration tells us now how this concentration propagates in time and space. And this results in a famous retention time equation that you see on the right button of the slide. And there is another quantity now introduced, which has to do with the dimension of our adsorber. We can get the diameter, the length, and also the flow rate in this T0. More or less, it's the residence time of a non-retained compound or of the liquid. It also is similar or corresponds to the length over the U. So now we have a a very strong equation of this equilibrium theory. It tells us at L, maybe at the outlet, how concentrations will show up there. We can illustrate the solution now, and I will use the Langmuirian isotherm, which has a decreasing slope of over the concentration, and that would provide now this curve, depending on the specific parameters of the isotherm, how the concentrations would elute. And for Langmuirian system, that would tell us that larger concentrations that are characterized by smaller slopes of the isotherms would propagate faster than smaller concentrations, which is a non-realistic situation, because we would have an overtake of larger concentrations against the lower ones, and discontinuities in the concentration profiles would result. And so such systems will not elute according to this equation, which is a wave equation. They would elute as a shock, where an immediate jump between the initial state and the final state will result. And so the initial state, which could be zero in both phases if the fixed bed is fully equilibrated, and the feed state characterize now the time of this shock. So for a nonlinear system, we have waves and shocks. They are characterized by the slope of the adsorption isotherm, or by a chord between two characteristic states, which are connected in this transition. So there is a lot of more information available. It all started with Aris Amundsen in the 1970s, Helfrich and Klein. And there is a wonderful series of 2 books with many details. Arvind and Marco wrote a beautiful review about equilibrium theory, and all these things are well documented. The bottom line is we need these 2 simple equations. We need to know when there are shocks and when there are waves. And then we need the parameters of the isotherm to predict these phenomena. So let me illustrate very shortly for a single component this in another plot. If this is an isotherm for a single component, we can now assume maybe the dashed line ends up at the concentration in the fluid phase of 2 grams per liter. And for a certain parameter set, here you see my German notation, we have a certain loading. And now filling the adsorber will follow this trajectory, this shock, where the slope in the isotherm is related to the retention time. And we have a clear predictive tool to predict the time of this first shock. Then maybe we stay there for a while, we don't change anything at the feet, but at a certain time, we start to desorb. And then we are at that point and head back to the origin. I'm sorry again. And the way back is now characterized by the slope of the isotherm. So we move along the tangent of this isotherm, and that generates this wave. If we would have started again an initially empty, fully regenerated adsorber with a lower concentration, in this case 1 gram per liter, we would generate now the red elution profile, where the retention time of this lower feed concentration, the shock related to this lower feed concentration, elutes a little bit later. The slope is higher here. That means we have, in a way, more capacity. Elution will be later. Then we stay at this 1 feed point, and at the same time as before, we go back, and now we follow the same wave, because we reach the tangent again at another point, and the dispersed fronts, the waves are the same. You remember probably my first example of the phenylethanol exactly has shown this phenomenon. So the Langmuirian part is by this well characterized. What would happen, and this is only a short excursion, if the isotherm would have a different slope. Sometimes that's called an anti-Langmuir, where the slope increases with concentration, which of course cannot go forever, but in certain branches of the isotherm. Then the opposite would happen. Then the adsorption front would be dispersed, and the desorption branch would be a shock or a sharp transition. Well-known knowledge, long time known in chemical engineering and adsorption, very important. Let me come now to a busy slide, which summarizes a lot of information. I think it might be a useful slide for those of you which really want to work in this field, because the right graphical solution is not too well known, and I like it a lot, and we use it very often. The question is, we have now two components that enter together an empty adsorber. In this graph, they are marked in red and in blue. In red is the component which is less adsorbed. In blue, the component which is better adsorbed. It's characterized by the parameters of the adsorption isotherm given on top of the plots, where the saturation capacity is, in this case, this is a toy example, 10 grams per liter. The difference lies in the two B values. In the initial slope of the isotherm, we have a selectivity of 2. You can learn this from here. So for this system, the breakthrough will happen like that. I gave additional parameters in this calculation, which you easily can reproduce yourself. I gave a residence time of 1 minute. The T0 is needed, more or less the size of the adsorber, and the flow rate sit here. And I packed them 50-50, 50% solid phase, 50% fluid phase. This is the dimension phase ratio. We do the analysis for 1 gram per liter each component, so it's a 1-1 feed mixture. In the right-hand side, you see the isotherms belonging to the mentioned parameters. The thin line in blue is the single component isotherm of this higher, better adsorbed component. The thin line in red is the corresponding single component isotherm of the second component, the less adsorbed, with the B equal to 1, B1 equal to 1. So the full lines are now the competitive isotherms. You see there is suppression. The blue single component moves down to this fat blue line. The stronger competition in this 1-1 mixture is on the side of the red component. Again, the fat line is now the resulting competitive isotherm as predicted by the competitive Langmuir isotherm. So the solution of the breakthrough fonts needs now to respect, it's written on the top, the famous coherence conditions. So if there are transitions happening, they are not independent from each other. In particular, in this case, the second transition that we see here will happen simultaneously, both for the red component and for the blue component. So we use this coherence condition in the framework of the equation before, and we are able to derive the equations that you see on the bottom. The dynamic behavior is characterized for this initially empty column by 3 numbers only, using equilibrium theory. One is the retention time of the first shock, TR shock 1, the second shock, TR shock 2, and the marked plateau concentration. I have marked it in green in the figure on your left. And the equations on the bottom tell us how these calculations, to which solution do they lead. Now, the shock 2 is calculated first here because it has to respect that there are 2 transitions happen simultaneously. And the transition for the red component contains the green marked unknown plateau concentration, so the degree of displacement of the first eluting component. Once this is known, the first shock can be easily calculated, because if we know the plateau concentration and we know that the first component travels more or less first alone through the adsorber. It takes all available space. The faster runner travels first on a single component isotherm. The calculation of this plateau concentration leads for Langmuirian systems to an easy to solve quadratic equation, which I have also given on the button, and that allows them to calculate the loading on the single component isotherm. So beautiful theory to read, and many literature references. You will see a few in the end. Let's look at the graphical solution, which is very helpful for quick estimates. So let's look first on the second transition. How is the second shock in terms of the blue component visualized? It must be this thin straight line connecting the thin blue line connecting to the fat isotherm line. So that information is now connected with the line showing in red between the single component and the mixture isotherm ending at the feed point. So we see there a parallel shift marked by this light blue arrow. Because they take place at the same time, their slope in this representation must be identical. And because we know the endpoint in equilibrium, we can use this parallel shift to find easily the plateau concentration, which we don't know in the beginning, but which is hidden in the isotherm information. Once we know this plateau concentration, the first shock is very easy to interpret. It's just now the connection to the origin of this component from the single component isotherm. So if you have the isotherms, you make these plots, you can easily calculate times estimates, you can calculate which degree of overshoot you can expect. So very useful and maybe interesting for you to use in your own work. An illustration how situation changes is here. If the feed is not anymore 1,1, what I did using the same parameters before is just increasing the feed concentration of the first component. That was the red one. I could have marked CF1 equal to 3 in red. You see it on the plot in the right-hand side. This is the final equilibrium state after breakthrough is complete. Whereas the blue component is in minor amount in the system, only at 1 gram per liter in this notation that I used in this example. And now we see an overshoot almost reaching 4. The 3 in the feed eludes for a certain time at the concentration roughly 4, which can be found easily by this graphical solution as the 2 times that you saw before already. Maybe another case, interesting for people also in gas phase or for systems which are very selective. When I go back in this slide to a 1,1 mixture, I want to separate 2 components in the same amount. I know the isotherm and I have a strong, it's a separation factor of 20 here. What I did, I just reduced the slope of the first component by a factor of 10. That leads now to this thin line, single component isotherm in red, fat line, the competition by the other one in blue, in red is a reduction. The blue component is not so much affected. And the resulting overshoot is much smaller. You see it in this small increase, in the small increasement in the plateau, which we see in both sides similarly. Nevertheless, there is competition around, and these calculations can be helpful to analyze such situations as well. The next slide is again full of information, and I need to be a bit fast to reach my plan, but I want to show you now the connection, the link to kinetics, and to show the strength of the thermodynamic view, which is maybe often the best to start with it. Here I have shown, in addition to the slide that you just see before, calculations, numerical predictions now with a more detailed model, which goes back to this axial dispersion coefficient that you saw before. I express it as a function number of theoretical plates. In the calculations that you see, I used quite a significant number, 500, and in a second calculation, 2000 plates. And you see now in these more curved, not rectangular profiles, the result of this kinetic phenomenon, that there is band broadening. Of course, for 500 plates, for the bigger dispersion coefficient, there is more dispersion, and much sharper remain the profiles for 2000 plates. What you see is the fixation of the position of the mean of these fronts at the times predicted by this very simple equilibrium theory. So from my viewpoint, thermodynamics are very often really dominant. We should look at them first, and then around these fixed position, kinetics need to be analyzed and evaluated. A bit the sensitivity of these thermodynamics and kinetics in another slide, where you are now familiar with the illustration, with the graphical illustration on the left-hand side. And I now played with two parameters. First, with a thermodynamic parameter. In this case, I increased the B value of the second component from 2 to 3. So I increased the capacity of the second component, the blue component. That means I go from the full blue line to the dashed blue line, 2 to 3. In the same way, I increase the competition on the red curve. If you see the red competitive isotherms, now the full red curve is above the dashed red curve. So I increase capacity of the second component. In parallel, I do for both cases an evaluation of the effect of a factor of 4 in the kinetic parameter. And you see the strong shift and displacement going from the full lines to the dashed lines in the breakthrough curves of the equilibrium model, and still the also sensitive but not so important in the first stage maybe effect of kinetics. So thermodynamics have a strong effect. I said this before. This is maybe a time or a chance to have intermediate questions if there are. I talked a lot. I need to drink a bit of coffee for a second while maybe Arvind can ask or find out if there are questions before I go on for a shorter final part.
Okay. If there are questions, we'd be happy to take questions now.
So I don't see anything. Arvind, you tell me. Otherwise,
Andreas, there was also a suggestion about the book by Duran-Basmedian as well. The one that is the little adsorption book, which gives a nice qualitative picture of these calculations.
Very good. I have a list of references in the end, and this beautiful book I have not included because I did not want to give such a long list. But there is a little adsorption handbook by Basmedian, very, very useful and beautiful source in this direction. Thank you.
Yeah, I don't see any other questions, so we can perhaps proceed.
Okay. Then I will make my screen big again and move on. So I have another thing to share with you. So my lesson is a little bit for graduate students, and also as a Czech lesson intended, many small experiences. So there is this famous analysis of areas in adsorption that many of you might know, but not all of them. That brings me back to my habilitation, where I made this plot. Let's look maybe first only on the adsorption side until we reach the plateau. CE stands here for entrance. I used feet in the notation before today. And the time that we can predict, provided we know the single component isotherm, is marked here. And any kinetic effect will spread around. And so the balls or the spheres that I gave here mark two sections, two sub-areas, which should be identical. So if you have an isotherm coming from somewhere else, and if you have a dynamic experiment, you can check whether you can predict the point of gravity, the mean retention time. These are all synonymous names. More rigorously, statistically spoken, this is the first moment of the breakthrough point, the first statistical moment, the mean. So check always these things. No? This is beautiful and simple to do for single components. You can do it, by the way, also for the desorption branch. It's more interesting sometimes and helpful also for mixtures. Here we have the same scenario that we had before, an overshoot of a breakthrough curve reaching the plateau value. And you see the area that is on top displaced, and the area that is retained, marked by plus and minus, in their difference must be equal to the adsorption capacity on the mixture isotherm that the system has. And similar things can be done for the desorption part. So look for areas, respect this as a very good source of information. This can be extended, and I guess Arvind has the idea to have a webinar also on measuring isotherms, on experimental techniques, and frontal analysis or breakthrough measurements are indeed one of the good tools. And if you do it, then very often you don't stop and the adsorber is fully equilibrated with the feed. You might go on a next step to a higher feed. Some people call it the staircase experiments. And then you see again the transitions, which will happen then at different times and will have different plateaus. By the way, if the column is not fully empty or fully regenerated in the beginning, the next plateau already will show you transitions for both components. And area balances are then again possible to check later results, to validate with independent experiments. I wanted to share this information because I don't see it used too often nowadays, and maybe industry is doing it and it's known a long time, but the young people sometimes need to get this lesson again told. So I have another part. Arvind might have liked maybe to talk more about this. Equilibrium theory is also hodograph plots and method of characteristics. And I just give a very quick flavor here. We have the coherence condition mentioned before that can be used to calculate so-called directional differentials in the hodograph space. So the breakthrough curves, if you look on the right side, the now familiar breakthrough curve, red overshooting curve, and the second transition for blue, they can be represented in a space where you plot C1 over C2, and you get rid of time. So there are certain corner points. The origin of this hodograph plot shown in the middle is the empty column. The last point where the curve stops is the feed composition. And in between this point marked with the almost 4 concentration of the first component, which is in fact the overshooting concentration, marks the transition, the intermediate plateau. And between these between these 3 points, these 3 states are 2 transitions. And for Langmuirian systems, one can prove that they are exactly straight lines, which can be easily calculated and analyzed. So to have a representation connection between isotherms and retention times via the hodograph space is for experts a very powerful tool. On the very right-hand side, you see also partly German slide where there is such a hodograph plot shown as with the blue middle part, but there is also shown a desorption branch. If you go back now to the initial part, the trajectories are predictable as well in this hodograph space. So the message is just don't ignore photographs if you are in this business and want to be quantitative. So I come a little bit to my final loop. I have considered a lot, but I left out many things, and some of you might miss them and might be disappointed. I will address 2, 3 more very quickly. What is the case if the isotherm is more complex, has difficult shape, maybe inflection point, anti-Langmuirian, Langmuirian mixing? And if there are more mixture models around, how do they go in the business? The question, of course, an obvious question is what happens if we have 3 components and more? How is the extension? And a big part which deserves special discussion is if the velocity is not constant. What happens if in an adsorber temperature changes, which is for gas phase adsorption very, very normal? Then we accelerate and decelerate fronts and need to respect, in addition to the mass balance, the temperature changes, which can be predicted by the energy balance then as well. So I will not address this, but roll over a few last slides. The anti-Langmuirian behavior, I think, is more or less clear to you already. We have discussed these envelope or these convex Hall operating line up and down for a Langmuirian system. On the bottom of the diagram is the opposite shown for anti-Langmuirian, and references are around there a lot. If there is an inflection point in the isotherm, in the left slide, the isotherm is a little bit shown as a thin line only. From this point A to point D, it goes down, then it goes up to G again. So this thin line represents now a more complex isotherm, which we know very well. And the example shown on the right corresponds to an adsorption-desorption cycle with a feed concentration between these 2 characteristic points, G and H. And the operating line for adsorption is always below. We saw that. And it generates this shock front shown in the elution profile. Interesting is here the desorption branch, which takes now the shortest connection between the feed state down to 0 again, and we call this sometimes the rubber band rule, because you can connect them now on top of the isotherm with a rubber band, and the shortest way is now a part following a shock down to point A. This is the steep desorption part in the beginning. And then we follow again the tangent along the slope of the isotherm, and we end up with a wave. So composite wave shock elution profiles for ad or desorption result and can be analyzed. Again, they form a good corset, a good positioning of these fronts. Extension to 3 components is very straightforward. For Langmuirian systems is a lot done. If we have 3 components, we have 2 intermediate plateaus. In the desorption branch, we see intermediate plateaus. You see it on the left side in the lower figure. And on the right side are published one example that we measured in our group, a PhD student, very systematically, where we see these transitions. Maybe if you concentrate your view on the lower left part, you see characteristic breakthrough fronts, 3 of them. Finally, on the top is the feed state, and then we go down to 0 again and have waves interrupted also by plateaus, by characteristic states. The last point I might address, if you don't dose long enough that you saturate the column totally, you don't reach complete breakthrough. Also, in this case, are analytical solutions around, in particular, again, for Langmuirian systems, and you can predict positions and shapes also in this case. So here, the feed concentration was much higher than the maximum. Loading was not long enough, and that's a typical situation in chromatographic, in preparative chromatography. So the last slide before I wrap up is maybe also new to many of you. The equations we derived some time ago and are not used very often. that's the inverse problem. And for quick estimations of isotherm parameters may be also useful. Let's assume you have a packed column, you know F and T0, you know the feet that was used to generate breakthrough curves, and you have measured for a binary system the two plateaus, the two retention times and the plateau concentration. And you are assuming now the Langmuir model as a primitive first guess model to be valid. And you are interested in the parameters of the Langmuir model. So the Qmax, the B1 and the B2. So you can then use the framework described to have analytical expressions for these three. As an intermediate, you have to calculate the loadings from the retention times. Everything is available for that. And then again, for Langmuirian systems, always a quadratic equation, which question you raise is the linking part. And here the quadratic equation is formulated and all the information is in green is there. And the three more or less pink colored symbols are in the end the outcome. So very quick estimate from one such profile shown on the top. So let me conclude. You have seen isotherm combined with the equilibrium theory of a fixed bed provide interesting equations, interesting tools. They allow us to address different questions. In a way, we have I call it in German das Korsett, so a corset for breakthrough curves. The positions are fixed, and we can distinguish between waves and shocks. Of course, there is more dispersion by kinetics, but for first evaluation, is it very powerful. It provides not a tool, but a tool also for parameter estimation. So with this, I have on the last slide some references. In fact, these are the references from this German primer, and in all of them is much more. I take the liberty in the end to point on this book on the button, Preparative Chromatography, together with Henna Schmidt-Traub and Michael Schulte. I'm an editor of it, and it just came out this month in April, third edition, where we put some efforts in updating it and also in bringing really new stuff. And there is a section on the topic I discussed today, which might be also of interest for you. In general, it's quite a broad reference in the area of preparative chromatography. So thank you very much. And I'm done and ready to take questions now.
Okay, there are a few questions, both here on Zoom and from YouTube. So I will just go in that order. So there was a question from Yogesh on YouTube, and the question is the assumption that you've made for equilibrium. Is that valid for single component or even multi-component? And what are the conditions under which this analysis can be performed?
Yeah, so I don't have the screen now anymore, but it's fine. You can hear me, all right?
Yep.
Yeah, okay. So the equilibrium is valid both for single component and for mixtures. I did not elaborate too much on the mixture equations. No? Everything is based on the assumption that at every instant of time and at every point in the column, equilibrium is established. So we connect the second phase, let's say the adsorbed phase, to the fluid phase, and we need to follow just one of the phases, and the other one is linked to it by the isotherm, and then it simplifies life, and we generate the solutions. When is it valid? Of course, it's more and more valid the smaller the particles used, because then intraparticle diffusion is reduced. And if I have a fast transport in the column, then I exclude external mass transfer resistances. So all mechanisms that can cause deviations are neglected here, obviously. But in chromatography, for example, where we use in well-packed columns very small particles, it's beautifully fulfilled. In activated carbon systems, you saw in the beginning my drinking water contaminant breakthrough curves, they are much more dispersed because we use bigger particles. But the assumptions are helpful for analyzing any system, I would say.
Yep. Thanks. The next question comes from Marco today. So the question is about the effect of flow rate on the shape of breakthrough curves and what that could mean for recoveries and purities when you have a binary separation, for instance.
Yeah, so the flow rates are included in these equations in a quite condensed form in this T0 in the dead time. So we bring in the flow rate in this residence time of the fluid phase, which can be short if you have a very high flow rate and everything happens fast, breakthrough will be fast, or slow. So if we change the flow rate, we change in principle external mass transfer situations and dispersion. So this effective dispersion coefficient or the plate number will be affected by that. Again, chromatography people know this as the Van Denter equation, and there are correlations around for that. So that's the key effect on the outer side. But I expect the equation is broader, good and important. Of course, flow rate is not constant in many systems. If you have strong adsorption, strong interaction, and for gas phase system, this is very valid. The equilibrium theory can be extended then, and for gas phase systems it is done. So I asked our chairman, Arvind knows that very well, and one should then consult the literature. But conceptually, assuming constant flow rate teaches the lessons I wanted to address today.
Okay. I'm going to take two more questions. So one comes from Shaya. So could you provide some insight for scale up? So when you now make measurements from small columns and when you're going to scale up, what typical parameters would you look for?
Scale up, of course, is the goal of engineering design. We start often testing in small scale. Scale up, if you take the same material, the isotherm should be the same. That would be not nice if we have the same material and we have to shift. Scale up shows up in this F factor a lot. You have seen the porosity, the packing. If you go to bigger columns and smaller columns, you might have differences there. If you have aspect ratio change, so the diameter to the length of a column, you might have also in the flow profile. I assumed in a one-dimensional model, that means in the radial direction of a column were no gradients. And that might be critical, even in very small columns, if you fill them with very big particles, where you have a low aspect ratio particle diameter to a column diameter, the flow profile might be very different from uniform due to different radial porosity things. And in very big columns, I think the thermal effect might be an issue affecting them back to the flow profile. So it's not the first thing I would say. For me, it's always the key to characterize the adsorbent quickly, well, having good understanding of the isotherms, the capacity, and then the design goes on. And the more and more you want to be more greedy and more precise, and maybe you need to respect really then more and more the economics, then you need to look closer at these things. But in gas phase, flow rate, of course, is a very important issue.
Okay, thank you. Probably that answered another question that came up as well. So the last question that I have is from Nancy Davia. So is the method valid for systems where diffusion is not negligible? So I will add an addendum to that. If diffusion becomes important, how do you take forward this analysis, or do you need more complex analysis?
Yeah, no, of course, then the precision is less, but I have shown in one or two of the slides the comparison between predictions of the simple equilibrium theory and the numerical solutions with the plate numbers. If I would have shown you the calculations, which are easy to generate, maybe for just 50 plate numbers. Now that would be big particles where intraparticle diffusion starts be limiting. The fronts would be even more dispersed, but they would be centered at the same position. So diffusion is the next step. It could be easily calculated, but I don't expect big surprises because I know already the positions from the analysis I have shown you now today.
Yeah, just to add on to that, in gas systems, typically when you're using larger particles, diffusion becomes a critical aspect to consider. Whereas in liquid chromatography, we deal with micron-sized particles. So we kind of approach the equilibrium limit better as compared to in gas systems.
Yeah, fully understandable.
Yep.
So
well,
if we reach the end of the question round, let me also say a few words. First of all, thank you very much that you joined, and we prepared. It's an initiative of Arvind. We have now much more speakers. I think we will cover the whole field and all problems of adsorption. And I invite you as a president of our society really to join, maybe give us also later feedback. We plan to see this a little bit as a primer of some basics, which are really essential to be successful in our business, but also to highlight current really hot topics in research, and both should be in this series of webinars. And considering joining the IAS, I would repeat the statement of Dan in the beginning, is very welcome. We are a healthy, active society, and you see we have interesting life organized, and everybody is very welcome. In particular, we look for young people. Then you will also learn that we organize huge, nice conferences. They are always fun, and the next one will be 2 years from now, hopefully without Corona, without problems, in the US, in the Denver area, and is in the planning stage. So with this, I would like to say thank you very much again for your attendance.
Thank you, Andreas, for your outstanding webinar discussing the connections between equilibrium adsorption isotherms and observed breakthrough dynamics of column operation. We'd also like to thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. Please join us again on Monday, April 27th at 10 p.m. in continental Europe, 4 p.m. New York, or 5 a.m. the following day in Tokyo for a webinar by Professor Fatima Rezai of the Missouri University of Science and Technology entitled Structured Adsorbents and Gas Separation from Formulation to Process Performance. I hope you can join us. There will be 2 other webinars next week, both at 10 a.m. 10 a.m. New York time, 4 p.m. continental Europe. Please follow our IAS Twitter channel for the webinar titles. Additional webinars are also planned for the week of May 5th. With that, we again thank you for joining this webinar and hope you will join us for future editions and for other events associated with the IAS and its members.